Thank you, Mr. Chairman. My name is Yukong Young. I'm from Rutgers University. And I'm going to talk about electrode stress. Electrode stress for improving frequency temperature behavior of very high frequency, ultra high frequency quartz resonators. And it's not working. Oh, I have to press this one, right?
Yeah.
This one, right? Okay. Yeah, the first question we have is, can the electrode stress be used to improve frequency temperature behavior of the quartz resonator? We know from past study that this frequency temperature behavior can be modeled using theory of small vibrations superposed on thermal strains. And we also know from previous studies that electrode stress on the surface of the quartz resonator can increase or decrease the resonant frequencies. So the question is this, we have an electrode, oh, sorry, I'm not used to this. We have a quartz resonator, and then you have this electrode. If you magnify the view, you have the quartz being sandwiched between two electrode films. In the past, under low frequency, this electrode film is usually modeled as a mass loading. When we go to higher and higher frequencies, we need to model it as a composite layer. Now, if we model it as a composite layer, it means that it has both mass loading and stiffness. And then when you have stiffness in the electrode, we find that when you change the temperature, there will be thermal stress and strain. When the electrode is just treated as a mass loading layer, obviously there's no thermal stress and strain in the electrode. And usually right now, currently, for the quartz thickness shear resonator, we have considered the electrode as just a mass loading for energy trapping. So moving forward, let me just talk a little bit about the electrode stress. This is a thin film electrode, and we deposit the electrode aluminum or gold on the quartz at a high temperature. We anneal it and then cool it down to the room temperature. By annealing, we try to remove the electrode stress. But since the electrode is a thin membrane, when you have some kind of change in temperature, the stresses in the electrode is primarily biaxial, no matter that it is anisotropic in the quartz. So we have just sigma x, sigma z, very low stress in the y direction, in the thickness direction. Now, if you use aluminum electrode, the thermal expansion of aluminum is about twice that of quartz. So if you look at this diagram here, when you raise the temperature, the aluminum tries to expand more than the quartz. And I mean, over here, tries to expand more than the quartz, so that due to the interface layer, the quartz will prevent the aluminum from expanding, so the aluminum will be under tension, the quartz will be under compression. Vice versa, if you lower the temperature, the aluminum will be under tension, whereas the quartz is under compression. So our study here is we want to look at the equations of incremental vibrations superposed on finite deformations, and we're going to use it to study this thickness shear resonators, vibrations of quartz crystals. We have 3D models of 1 gigahertz rectangular cantilever mounted resonator, which looks like this. We have also made this device. We are going to look at both composite plate and mass loading to see what the difference is, and we use different electrode materials to see if we could change the frequency temperature behavior. And also we have 3D model of a lower frequency HF resonator, which is 10 megahertz. The equations are nonlinear. These are equations, incremental displacements, incremental vibrations that are superposed on thermal strains. Just to remind everybody here, these are the strains from temperature. These are the thermal displacement, thermal deformation gradient, and thermal strain at the initial state when we change the temperature. So these are the equations that we have put in our COMSOL model for this study. And first of all, when we change the temperature, we need to calculate the stress. And we have calculated the stress in the x direction. And if you look at this here, when we use aluminum as the electrode, when you change from 25 degrees Celsius, we see a negative slope, which means that at higher temperature, the aluminum is under compression. At lower temperature, the aluminum is under tension. And if you look on this side, this is for the plate stress. When the aluminum is under compression, the plate will be under tension. It's the reverse. So whenever you have the stress in the electrode negative, you will have positive stress in the plate. Conversely, if you put in chromium, which has different material properties, we see that sigma x, when we change the temperature, is a positive slope. And with that, the plate will be negative slope. And you could also look at the other state of stress, since it's biaxial, in the z direction. Very similar to the previous diagram here, except that in the z direction, the amount of stress is lower. Okay, so let me just repeat this. When the electrode stress is positive, plate stress is negative, vice versa. The stress in the aluminum electrode on the quartz versus temperature has a negative slope. The stress in the chromium electrode on quartz versus temperature has a positive slope. Now, with this in mind, when we look at this 1 gigahertz resonator, this is for mass loading. Now, if you design this resonator according to mass loading, it looks very nice. But when you go and build a resonator using aluminum electrode, we see that there is a jump in the frequency change. So in order to compensate for this, what I'm trying to say is that we have to use composite plate theory to design this plate resonator, because you have a rotation of the frequency temperature curve. This is a clockwise rotation. Conversely, if you use chromium, this is when we use chromium, about 0.04 micron. This is for mass loading, which means that there are no thermal strains. For chromium, it rotates the frequency temperature curve counterclockwise. If you use titanium, it tries to rotate the frequency temperature curve counterclockwise, but not so much. Far less than chromium. So we have done also studies whereby we use two metals. This is the curve where it's just mass loading without any electrode stress. This red curve here, let me just go to this blue one, is one with the aluminum. So this is the, if I could see, yeah, this is the blue one with aluminum. And if you put in a little bit of chromium, 0.02 micron, half of the aluminum thickness, we can rotate it closer to the mass loading. So this will improve the frequency temperature behavior. If you put titanium, it will not rotate it as much as chromium. So if you have aluminum, it's always good to put in some if you have aluminum electrode, it's always good to put in some chromium electrode to improve the frequency temperature behavior. Adding a thin layer of chromium will improve the frequency temperature behavior. Now, if you have a low frequency resonator, say 10 megahertz, the electrodes do not affect the temperature behavior at all, actually, not much. If you look at these curves for various types of metals, the frequency temperature behavior does not rotate. Some people will say that, well, there are some changes here. These are due to spurious modes. So with that in mind, let me just summarize what we have learned here. For ultra-high frequency quartz resonators, we have to treat it as a composite plate of quartz and the electrode film. Since the ratio of the electrode thickness to the quartz plate is significant, and the electrode film will rotate the frequency temperature behavior. The quartz-aluminum composite plate rotates the frequency temperature behavior clockwise, while the quartz-chromium composite plate rotates the frequency temperature behavior counterclockwise. And titanium is a very good electrode material for our study because it does not rotate the frequency temperature behavior that much. And finally, the last conclusion is we can try to improve the composite plate by adding another material such as chromium if you are using aluminum to rotate the plate counterclockwise closer to what we have in mind. Thank you.